So there's two main themes that we want to get to. We're going to deal with predicting boiling or melting points first. They always work the same. So if something has a higher melting point compared to something else, it always have a higher boiling point. And then we'll deal with solubility. So just a quick recap, boiling point is really a measure of how much energy we're going to relate that to temperature it takes to separate molecules. So if something has more forces, more intermolecular forces, it's going to have a higher boiling point because it's going to take more energy to overcome those forces and separate them. That's the fundamental principle we used in Chem 20 and we'll use here. So I want to go through these forces fairly quickly because you have to identify what forces are in that molecule and then compare them just like you did last year. Okay? So the first force to consider that everything has is London dispersion forces. This is caused by random movement of electrons. Every molecule is going to have electrons, it's going to have protons, there's going to be an attraction between the electrons in one molecule and the protons in the other. Okay? So again, everything has London dispersion forces. So even something that's non-polar, like an iodine molecule, okay, that's non-polar, there's no positive or negative end, but you know, there's electrons in that dash, there's other electrons in the molecule. Okay? These electrons, you don't think of them as just being in one point, think of them as waves spread out all over the place. They can randomly be at one side or the other for a millisecond or fraction of a second, okay, which can cause an attraction between one iodine and another iodine. Okay, so it's London dispersion forces that can hold one of those to one of those. And we see the same thing in non-polar molecules like methane. Well, if you remember last year, if you saw symmetry, if you had a central atom and everything around it was the same atom and you had symmetry, there'd be no positive or negative end, and you see that in methane. Okay? The only thing holding one methane to another methane are these London dispersion forces. Okay? Random movement of electrons here will be attracted to positive charges or the protons over here. A much stronger or a potentially stronger force are dipole-dipole forces. These are now not temporary little poles, positives and negatives, but permanent dipoles that would be holding two molecules together. I'm going to draw methanol. And we have a polar bond. We used arrows like that last year to denote when a bond was polar. Oxygen is much more electronegative than hydrogen. So the oxygen has a greater attraction to these two electrons. Okay? In general, the non-metals close to the noble gases, they have high electronegativities, fluorine being the highest, and you see lower values in group 1 and 2. So we kind of have a pretty good extreme here between oxygen and hydrogen. We have a very polar bond. So that's going to cause the OH on one methanol to be attracted quite strongly to the OH of another methanol. So there's really just these two types of forces. Hydrogen bonding is a special case of dipole-dipole. Chemists have found that when you have three types of dipoles, they're unusually strong. They're stronger than we would expect just following a trend in the periodic table. So there's three types are OH, NH, and HF. And since this is organic chemistry, unlike last year, we're really just focused there because we're going to see oxygen show up in our carboxylic acids, and we're going to see it show up in our alcohols. Okay? So you have to watch out for hydrogen bonding in those two families. So I'm not going to redraw. By example above, is dipole-dipole that happens to fall into this hydrogen bonding category also. So I wanted to do this quick. It's meant to try to pull back some of that information. Hopefully it's coming back to you from Chem 20, these three forces. You're going to see lots of examples coming up. So I'm going to rank the following from lowest boiling point to highest boiling point. We've got hexane, we got methanol, and we got butane. Okay. Now I don't want to draw them. I just want to use the names to figure these out. Okay. It might help you to draw them sometime, but hopefully those are, they're simpler structures. We can do this without the name. Okay, I'll just highlight. So this is hexane. I can get the molecular formula quickly, and that's going to help us. So that's C6H what? Why are you saying that? Yep. So we have an alkane, so it's 2N plus 2. Hex is 6 carbons, so he did it correctly. He doubled the 6 plus 2 is 14. We have another alkane, a C1. Now we don't write the 1, but I can still double it plus 2, and that's H4. Okay. And butane, C4, that's another ane, so double 4 is 8 plus 2 is 10. Okay. Now all of these are C and H only. What was said in Chem 20 about C's and H only, no matter how big? What about polarity or forces? They're always nonpolar, correct. And that's kind of what led to these weird little papers here. Way back several years ago, I said no matter how big it is, it could be a C100 H2O2 and it would still be nonpolar. And somebody went and made C100 H2O2 and put it up. Last year's class did this one. I don't know what this is. I think it's C200. So you can't really see, but these are all C's and H's. This is just a great big long hydrocarbon. So all of these are C's and H's only. So all of these have London dispersion forces only. So that's the only force we need to look at. And when you're trying to separate how strong is London dispersion forces, all you care about is the number of electrons. And we don't need to count electrons. The C6 is going to have the most. It's got the most C's, the most H's. That'll have the most electrons. So it'll have the most London dispersion forces. So it's going to take the highest temperature to separate them. It'll have the highest boiling point. Now we need to do these from lowest to highest. So this would be our third. That's our highest. That's our last on our list. Okay. The lowest forces, so the one that would come first would be the least electrons. Okay. And then butane would come second. Okay. So we need to get a list of forces. We only have to worry about London dispersion forces in this case, C's and H only. So all those aliphatic hydrocarbons, anes, enes, ynes, cycloanes, cycloenes, even benzene, it's not aliphatic, but it's C's and H only, nonpolar. Methanol, we're going to have a lot more forces now. Okay. We've got one carbon, okay, with an OH, ends up being CH3OH versus methane diol, and it's got two OHs in it. So if we think of our forces, we're going to kind of have to figure which one has the most forces. Okay. Well, let's start with London dispersion. When you're trying to separate forces, I'm going to do the same as last year. It's these two that we look at first, London dispersion and hydrogen bonding. That's going to pretty much separate it out. Okay. So London dispersion, which one would have greater LDF? Which one has more electrons? The diol. Why is it this one? It's got more atoms in the C and the C is a tie. The H count isn't a big difference, but there's 2 O's in this one and only 1 O in that one. Okay? So the big difference is the extra O, which brings a lot more electrons. If we look at hydrogen bonding, this one has 1 hydroxyl group. This one has 2. It's got double the hydrogen bonding. I'm going to go 2x, double. So we got more LDF on this side. We got more hydrogen bonding on that side. This one's definitely going to have the higher boiling point. Okay? This one will definitely have the lower boiling point for 2 reasons. So the lower one we had to do first, so that would be methanol. The higher, the second on our list, would be the diol. So I wanted to do a couple examples, try to get your mind back into doing these lists. The best way I find for students to tackle organic chemistry and forces is to do it by family, because you tend to see the same forces in the same family. So that's how you should think of this. So this slide, I'm going to go through the families. So first, we have the anes, the enes, the ines. I didn't write it, but the cycloanes, cycloenes, same, benzene, all the hydrocarbons. Okay, all the hydrocarbons are C and H only. Okay. So that means all of these are LDF only. Don't even think of any other forces. So you're just looking at electrons. Okay. Okay. And you could be asked to rank hydrocarbons that you can't name. Okay. So I could have you, I could include a C20, H42. And ask you to compare that to a C12, H, doesn't even matter. And ask you to compare. And they're actually different families, but you don't care. C and H only, LDF only. The one with less electrons will have less forces. So that takes care of a lot of families, all those hydrocarbons. The only sort of quirk you have is if you have isomers that have the same molecular formula. Okay? So maybe you're looking at a couple C4H 10s, okay? And you're trying to decide which one would have the higher or lower boiling point. We look at the more branched one will have the lower boiling point. Okay, so this is only if you're kind of a tie for the number of electrons. So that'd be comparing, I'm going to leave the H's out. You're comparing, there's one C4H10 isomer, butane. And it does zig and zag, but it's relatively straight. So 2 of them can get really close together, and it causes a greater force. If you compare that to a methylpropane isomer, this is the more branched version. And hopefully you can see that several of these can really line up close to each other. When you throw the branch in, it pushes the molecules further apart. The forces are now further apart, or the charges, I should say, are further apart. So it minimizes the force. So if you have a tie with your number of electrons, look at the more branched. Okay, this rarely comes up, but could come up. And you had the same speech last year in Chem 20. Organic halides. Okay, my theme is what forces, if you have an organic halide, what you should be thinking in terms of forces. You've got 2 possibilities here. With organic halides, you should be slowing down and really looking at the structure. You could have tetrafluoromethane. And this is going to be LDF only. We've got 4 polar bonds, but they all cancel each other out due to symmetry. The other option you're going to have is when they don't cancel. Don't even worry about drawing arrows and figuring out which bond is more polar. Once you have a halogen and you don't have that perfect symmetry, you're going to have LDF because everything is that, and you're going to have dipole forces. Okay? So with organic halides, you got to figure out which category you're in. You should be, kind of expecting this on a test or quiz, that you don't see an organic halide and say, oh, tons of forces there. Well, no, it may not have a dipole force. Alcohols, we're going to go back to only one option. I did methanol, the simplest alcohol, but there's no way alcohols are bent. Okay? I've been drawing them bent all along because as a teacher, I know they're bent. I teach Chem 20. My brain has to bend them. That's how they come. This bent nature, even if you have a second OH, they never cancel each other up. They never line up. So there's London dispersion forces, there's dipole forces, and there's H bonding, and these are always here. So you see an alcohol, you're going to that list right away. So alcohols are simpler. You see an alcohol versus an alkane that's one carbon long, you're thinking higher forces for the alcohol because you know it hydrogen bonds. Last, carboxylic acids, and one reason they're last, they have the most forces. So that's the simplest carboxylic acid, just one carbon. Okay? Methanoic acid. Okay? They have London dispersion forces. They have dipole. They have hydrogen bonding. Because you've got this hydroxyl group, but you also have this highly polar carbonyl group. So that's carbon with YL added at the end. Now, carbonyl is not a word that's in Chem 30. I think it's a poor idea that they don't include it. I think you should be familiar with, because you have carboxyl, which is the whole thing. Carbonyl is just the C double bond O. Okay, and they're similar, like they're similar letters. There's just a slight difference between the two. So I will never assess you on carbonyl, but that's a C to O, very polar. It's got a double bond. So with the carboxylic acids, you've got the alcohol and this highly polar bond. So carboxylic acids have the highest forces. Okay? Plus you have the fact that some of these H's can come off and you can have a full extra electron sitting here, which is going to greatly increase the forces. You've got a full negative charge that's going to be really attracted to protons. Okay? So these are by far the highest forces. For relatively similar sized atoms or molecules. So that's the families in terms of forces focused on organic compounds. I'm going to take C. I don't want to have the C discussion today due to time. So these are for you to work through. Now, in terms of solubility, for Chem 30, you need to figure out when is their high solubility. We're not going to do the middle, where there's a little bit of solubility. Okay? And the textbook is written that talks about the middle. Okay? And there's some homework questions about the middle, but your exams will focus on high solubility. And you get those in two extreme cases, when you have a similar substance in a similar substance, which is where this like dissolves like comes from. And it only works for the two extremes, the two high solubility extremes. Okay? So to get high solubility, you can have combinations of two polar substances that have London dispersion forces only. Okay? So if you put propane in ethane, okay, they would both have LDF only, and they'd be highly soluble in each other. Okay? And they're both hydrophobic substances, water-fearing substances. The other possibility that gives very high solubility are two very polar H-bonding substances. Water hydrogen bonds. Okay? You can put an unlimited amount of ethanol, okay, that hydrogen bonds into water. You could put 10% ethanol in water. You could put 90% ethanol into just 10% water and still dissolve, because the hydrogen bonding in one molecule will always be attracted to the hydrogen bonding on the other. So unlimited solubility in two hydrophilic substances. So I mentioned orally a couple examples that create high solubility, but I want to write out a couple examples. So that's methanol. If you take methanol and you put it in water, you're going to have an incredibly high amount of solubility. If you had 1 liter of water, you could put 4 liters of methanol in it, okay, and it's going to be soluble. Okay, an incredible amount, very, very, very high solubility. Okay. Or second example, C8H18 in C7H16. So we have an alkane, octane, and that's heptane. Okay. They're both hydrophobic, they both have LDF only, and you can put almost any combination of this one in that one. Okay. And this is what you see at a gas station. This is octane. If you've ever looked at a gas pump, that's what you see the word octane. Okay. The gas you buy isn't 100% octane, it's a bit of a mixture, and depending, you've got regular and plus and supreme, and there's, some of the differences between regular, plus, and supreme is the ratios and how straight chained all those hydrocarbons are. But they're all highly soluble in each other. The company putting the gas mixture together doesn't have to worry about solubility. Okay? They can put any amount of octane and heptane without any worries. Okay? So we're moving into some of the applications of these physical properties, and that's really where Chem 30 wants to go, or wants students to apply their knowledge. So we're going to talk about solvent extraction, and then we'll talk about fractional distillation, and then we've completed this section. So solvent extraction, we want to extract something. Okay? Maybe you've SO by mistake spills a bunch of octane into the ground, and they want to extract that octane out of the ground. One method is solvent extraction. Okay. Adding a solvent that will be highly soluble to whatever sample you want to extract something out of. Again, maybe it's soil. Okay. You've spilled a lot of octane. I'm going to draw a slightly different example, a positive example, something that's done a lot in Alberta. This line is the ground. There's lots of oil sands down in the ground in Alberta. And one method to get that oil sands out, instead of taking trucks and digging up the ground and literally scooping all that oil and refining it, is to solvent extract it out. So if you put a pipe system down into the ground, and if you put in a solvent that has the same forces, some solvent that is LDF only, down into the ground, that the oil in the ground can dissolve into that solvent, and then you can flow that solvent back out. Okay. They don't do this just like this, but this chemistry works. It just isn't good enough engineering-wise you can make money. Okay. They have to do some other things. One issue is this oil is really, it's kind of like a solid, so they'll often pump heat or steam down in the ground to help warm the oil sands up to get them to flow and then try to get it out. But solvent extraction at its heart is using something that is going to dissolve what you have in the ground to get it out. Okay. So this would work just the same if you'd spilt a chemical here and you want to try to extract it out, put in something with the same forces and extract it. So that's the heart of solvent extraction. Okay. This tends not to get assessed as much. It's in the curriculum. What shows up every year on your diploma, so we're a little more biased, to talking about is fractional distillation. Now that's going to be on the next slide. I just want to talk about solubility of alcohols, and then we'll do the most important maybe slide of the day. So don't lose steam on the last slide because it's the one most likely to be on your final exam. Solubility of alcohols. So I've drawn out a alcohol, a 4 carbon long, so butane 1-ol. And then I'll address the purple later. You don't even worry, but you can get the purple down in a minute. In an alcohol, all of the hydrogen bonding forces are coming from this part of the molecule. The C and H repeating part of the molecule doesn't have any polarity to it. Okay? I'm about to make a statement. I'm not saying the molecule, I'm saying that piece is nonpolar. So we have this polar end and this nonpolar, often referred to as a tail. And the longer the alcohol gets, the longer that nonpolar tail gets. Okay? Now water is going to be highly attracted here. The polar end of water, or the OH of water, will be attracted to this polar end. Water will be repelled by this nonpolar piece. The longer the alcohol gets, the longer that nonpolar piece gets, the less soluble that alcohol will be in water. So the smallest alcohols are very soluble because they don't have much of a tail. But a decanol, or decane 1-ol, a great big long 8, 9 carbons at the end all by itself will not have a very high solubility. The smaller the alcohol, I'm referring to the carbon chain, the greater the solubility. The extreme being methanol, is very soluble, very high solubility, almost infinitely soluble, because there's no CH tail at all that's going to repel water. You would, yeah, you would start, if a really long alcohol, you'd start getting some polarity in nonpolar substances. Now, you're not going to get one big application of this type of thinking is if you buy a soap and wonder how soap works, they have really polar ends and then really long nonpolar ends, because soaps are meant to mix with everything. So you put soap on your hands, the long nonpolar piece of the soap will bind to the oil on your hands. The polar end of the soap will bind to the water. So soap will stick to the oil on one end and the water on the other and help remove the oil off your hands into the water and send it down the sink. So soaps or surfactants, have this dual nature role. And again, that's how they work. They can sort of stick to both. You're not going to get tested on surfactants. They're not in this course. Soaps aren't in it, but it certainly connects to what we're talking about with alcohols, with these sort of two ends. Okay. Tri-fatty acids have this. If you've seen tri-fatty acids in bio classes, this carboxylic groups at one end or carboxyl groups at one end and long CH chains at the other. Okay. So let's get into, we're going to need a few minutes to get through fractional distillation. I don't think I've ever seen a diploma that didn't have a fractional distillation question on it. Okay, so a little bit of theory, and then we'll get into what the setup looks like. Okay? And this directly connects to the oil industry. This is done, all the oil that's produced anywhere in the world has to be separated. Okay? The oil that comes out of the ground cannot go straight into your car. It would not work. We have to separate it, sell some of it to the airline industry, some of it for diesel trucks, some of it for automobiles. Okay. So crude oil contains hydrocarbon chains anywhere from C4 all the way to well over C20. Any thoughts on why you don't see C1, 2, or 3 in crude oil? So when oil is coming out of the ground, there's no C1, 2, or 3. They're gases. Yep, absolutely. So that'd be the natural gas industry. But we're talking about the oil industry here. So no C1, C2, C3. C4 butane would be remember in Chem 20, you had that mystery gas that you had to fill up a tube in the sink? It was butane from a cigarette lighter. So that's the first liquid. Okay. All of these oil products are just held by London dispersion forces. So their boiling points are nicely separated by the longer the oil product gets, the higher its boiling point. Okay? And that's the property. We're going to use heating and their boiling points to separate all of these hydrocarbons out so we can sell them to different customers. We've got one slide. I'm going to actually draw a fractional distillation tower, or you're going to draw it. I've put up a graphic, and then we're going to talk about the science behind it. We don't see these down south very much, but if you go to Edmonton, there are several refineries in Edmonton, and you'll see large towers that are fractional distillation towers. Is everyone okay? Are you ladies okay? And again, the notes will all be on D2L. So This is the heart of a fractional distillation tower. I'd like you to draw what I'm going to put a box around. So we've got a tower. We've got these baffles, which I'll talk about in a little bit. We've got crude oil coming in near the bottom. We've got a heat source. And then we've got this cooling. As you go up the tower, it's getting colder and colder and colder. So pretty much everything is going to boil here. And as it goes up, it's going to start condensing and turning to a liquid. And depending on its boiling point will affect how high it gets before it cools to a liquid and is filtered off. Don't worry about all of these. I want to talk about them, but they're not something you need to memorize. And this graphic will go on D2L. So get down the box, and then I want to talk about the chemistry and what comes out where. The baffles or... think of like a C5 is going up and then eventually cools, turns into a liquid, and it's going to fall and be collected here and be sucked out at that level. Yeah, it'd be similar to that, but this is that's a distillation of one thing, where this is a distillation of, it's a more complicated version of the exact same principle. So again, don't worry about these. I'll mention the words. You don't have to memorize any of them. I think it's nice just in context. They're terms you've heard of, but you need this tower. So I'm just going to emphasize even more that you're sending in sort of the raw crude oil, which is a mixture, in near the bottom. Okay. And you've got a heat source. So you're going to turn all of that close to solid or liquid. You're going to turn most of it into a gas. Now, some of the crude oil is going to have such a high boiling point and that it's never going to boil. It's just going to stay a liquid. So the parts that just never boil are going to come in and go down and come right out the bottom. And those are going to be your tars, asphalt that's used for a road. They're never going to boil. They'll just turn to a liquidy goo, come out the bottom, and be sent off. Really, to roofing industry and roads would be pretty much the main spots you're going to send those products. Everything else is going to boil and start working your way up. They're going to pump more and more in, more and more gas. It's going to want to drive all the gas up. Okay. And the compounds that are just able to boil are going to go up a little bit and cool. And then they're going to turn to a liquid, fall down, be collected by the baffles, and sucked out. So the next highest would be something like wax for a candle. It will barely boil, it'll quickly condense back down, and those will come out next. Okay. The highest boiling points, your C2, C3, C4, C5s, very high boiling points, they're going to go up, and as it cools, they're going to stay a gas, and near the top is where they're going to come out. Okay. So the very top would be your C2, C3, C4s. You might have a little bit of these gases trapped in the oil. Okay. And they'll go right to the top. Okay. Next down will be around your C8s. I'm just leaving the H's out. I'm just talking about the carbon count. You know, and the C8s, the C7s, the C9s are going to go to the gas, you know, to be sold as gasoline. A little bit bigger, a little lower, and those will be sent as diesel fuel and jet fuel. So you're getting the smallest hydrocarbons are going to the top. The larger the hydrocarbon, the lower down it's going to come out. And that's the main question you'll get. Okay? You might be asked to rank from the top to the bottom, where might you find C2H6, C7H16, and C20H40? The smallest is going to be most near the top. This is a little bit bigger, middle, and then the largest will come down near the bottom. Okay. You should also recognize this type of tower setup as fractional distillation. You could get a picture of this tower and ask, is that fractional distillation? Is that solvent extraction? Or is that maybe a couple words that are not even things covered in the course? You need to recognize this type of setup as fractional distillation.